All right, so a recap of where we are. We talked about supervised learning, talked about deriving rules and arranging them into trees. We talked about how those trees are susceptible to overfitting. And we talked about one way of combating overfitting is to use ensembles of weak learners and combine their results to form a strong learner, and gave one example of this in random forest. We also mentioned that one disadvantage of these ensembles is they become pretty difficult to interpret, right? Because it's a big vote among a bunch of smaller models, and so you're not quite clear where the decisions are coming from. And random forest had one way of attacking this, in that as you build the random forest, it was producing an importance measure for the variables. Right? So if particular attributes were more influential in the decision, you would get a measure of this as one of the outputs. And then we talked about k-nearest neighbors, which was a change in that it used numeric attributes. And continuing that, we're going to talk about gradient descent and some applications of it. Okay. So this, remember the three components of a machine learning solution is the representation of the model, the evaluation of that model, how you tell how well it's doing, and then how you optimize the process. And so the gradient descent is an optimization method that's applicable in a lot of different contexts, and that we'll touch on at the end. Okay, so in a nutshell, what you're doing here is expressing your learning problem in terms of some kind of a cost function that you want minimized. And starting at some initial point, you're going to roll the ball downhill until it settles in a trough. And so this process describes how to walk downhill. It's not really a roll, right? You're going to take steps, and that turns out to be one of the difficulties with gradient descent. Okay. And so some situations you can sort of design offer a guarantee that the minimum you find will be the global minimum. Other times you don't. And so getting trapped in local minima for more complex problems that we won't go into too much detail on is another potential weakness of this method. Okay. So the problem we're going to be thinking about here is no longer classification, although we'll mention how you can use this for classification at the end. But we're going to think about just regression. Okay, and so regression can still be used as a prediction task, and we think about sort of fitting a line to data, but the point is that you might use that line in order to make predictions of the outcome value, the response variable, given the inputs down the road. Okay, so a regression line is a predictor. Okay, so rather than a discrete class variable, we're maybe talking about a response variable that's continuous. Fine. So in this case, we'll take the very simple case of just a single input variable, but in throughout this, we're going to be thinking about an entire vector of input variables, and that vector you can think of it as a row in a database. Okay. All right. So imagine we have these points scattered this way, and you can see that this is a pretty cleanly produced data set where there is kind of a regression line that exists that probably describes the data pretty well. And in fact, that's not a surprise because I sort of generated to have that effect for illustrative purposes. So the process here is we're going to imagine that there is, that we split the data first into a training set and a test set, and that's always the first thing you want to do if it hasn't been done for you already. And here we just split them half and half. And we talked to a couple of segments ago about various ways to do this, but here we're just going to train on one half and test on the other. And further, I've scaled the data so that the original domain here of -10 to 60, or really 0 to 60, and some kind of range of 0 to 600 is scaled down to variation around 0. This is actually a little suspect what I did here, because I scaled the data all at once and then split it into training and test data. And so the test data sort of influenced how the training data was scaled, which is typically a no-no. Okay, so you may want to scale them sort of separately. So how does this gradient descent work? In this plot, what we have is the two parameters for the regression line, which are theta 0 and theta 1, and it's the y-intercept and the slope, essentially, right? These are the two parameters for a single line. This is the equation down here. I refers to the iteration number. Okay, so this is really iteration 0 that we're looking at, or really the difference between iteration 0 and 1. So we started this process off at this point, and we picked that point randomly. Right? And there's various deterministic ways to choose a starting point, but in general, the fact that you have to decide a starting point is one of the weaknesses of gradient descent. Okay, so we start off at a single point, and then we found the direction of steepest descent and took a step in that direction. So the cost function here that we're trying to minimize, this says that the response variable y minus the function applied to the input variable, and here the function is just a linear regression of intercept plus slope. Take that difference and square it and add them all up for all the data points. Right? That's the total amount of error that you received by trying to explain all the data with this particular regression line that we started with, this first starting point. And so we compute that gradient, and I haven't shown on this slide how to do that, but you complete that gradient and jump down quite a bit, right? The error goes down a lot in this first step as we walk from here to here in this parameter space. So now we've gone from one regression line to another regression line. Here's the first regression line that we started with, and we just kind of got lucky that it already is kind of in the right direction. We may not have. It could have gone this way. All right. So the next slide, we take another step, and the error goes down a little bit more, and we take another step towards the minimum over here, toward the center, and we've got another regression line that has rotated slightly, so it's closer to what we intuitively think will be describing the data. And we can keep going with this and keep stepping down, and the regression line gets better and better and better. The error goes down, right? We're finding a local minimum in that error until we decide that it converges. When the difference between the error in iteration I and the error in iteration I plus 1 is less than some threshold, okay, then we decide that it's converged. And in fact, in this case, it looks like it did pretty well in that it got what we see as sort of the minimum here. And this line looks like it describes the data pretty well, which we can see on the next slide. So again, each one of these lines, this line is perhaps the slope and intercept, right? These two parameters, theta 1 is theta 0 and theta 1 from iteration 1, while this next line is the theta 0 and theta 1 from iteration 2. Okay. So at each step, we form a new line, test how well it describes the data, and proceed. But what I haven't said is how we figure out what direction to actually walk in, nor how far to walk. All right, so let's think about that. So how does this work? So each parameter is going to be updated with a new value derived from its old value, plus taking a step in the direction of the gradient. Okay, and so in these plots, remember, this is the coordinate pair theta 0, theta 1, right? That's the space we're in. And at iteration 1, the point is here, and at iteration 2, the point is here, and iteration 3, and so on. Okay. So in order to get iteration I plus 1, we're going to take the same value, the value of the parameter iteration I, and add this offset term. Okay, so what's going on with this offset term? So this is the learning rate, which is just the step size. How far are we going to go in that direction? Okay, and this is usually a small value, maybe 0.001 or something. Okay, but really it's application specific. It's a bit silly to even state what it should be. However, I didn't notice that in this example I did scale everything down to a value. So 0.001 on scaled data may not be an unreasonable thing to use as a default. And so this operator is the partial derivative with respect to theta 1. And if you remember, a little bit of college calculus, the sum of these partial derivatives is the gradient. And so we're just doing one of these, partial derivative with respect to one particular variable. Okay, and then j is our cost function that I haven't shown yet. And j will be a function of these parameters as well as a function of our data set. Right? We're going to take these parameters plus all the data set and compute some new cost. So blowing up j, so this is our model at iteration I. Right? Remember, we're trying to compute the new value of the parameter at I plus 1. Apply that model to the data instance x, subtract the true value, the correct value y, and that's our error, square that, and then add it all up for all possible values in the data set, which is what k is, right? So we're going to run over all of our data points, check the difference, square it, add it all up, that'll be the value. And actually divide by 2 here, but that's more just to make things work out. So you'll see that a lot. It's divided by a constant factor, so it doesn't actually change the direction at all. Okay, and so now we just need to differentiate this with respect to the parameter that we're updating, in this case theta 0. Okay, so this is elementary college calculus, but just to show the steps on one slide. push the partial derivative through the sum, and then apply the chain rule to get this two factors. And then remember that h, our model, is actually just a linear model, so we're multiplying the x value times the slope parameter, adding in the y-intercept. And the only term in here that involves theta 1 is this theta 1 times xk. So the other ones don't involve theta 1 at all, so we can just drop them. Their derivative is 0. And so this just simplifies to xk itself. And so h of xk minus yk times xk is the update rule that we're looking at. So this is just sort of putting the starting point and the final point together on one slide. So the overall update rule looks like theta at I plus 1 equals theta at I plus the learning rate times the sum of the value that we predict for xk minus the true value times xk. And so overall what you say here is, while not converged, apply these update rules. Update theta 0 and then update theta 1. Okay, and then check for convergence. And so that's the program that you could write if you were going to implement this by hand. So one detail here, why is theta 0, for the theta 0, why don't we have this multiplied by xk? Well, the reason is that because it's the y-intercept, there's not an x value to multiply by, so it's actually just assumed to be 1.0. And in fact, you can think of this as adding an extra. If you've got a single attribute, right, our x values, and we're trying to predict y from x, we can think of it there actually being two attributes. One, our x values, and the other one being a constant attribute, where every single instance in our data is just the value 1.0. So it has no effect on the learning, but it allows us to have, an x variable for every parameter. So there's sort of a trivial x0 right here, and you can assume that x0 is always 1. Okay. In which case, then it would also appear out here. So some questions that arise from here, there are still some parameters to this process that have kind of leaked in, right? There's this initialization step of where we decide to start the process, and we have to choose that point by some mechanism. Okay, so you might have sort of small random values, or you might pick always the same point, and random, as usual, gives you a little bit of robustness. Okay, and then you also need to decide the step size, and this procedure is, notoriously sensitive to choosing a step size. So if it's, we don't really roll, we're not doing a kind of a continuous fall down the gradient, we actually have to jump, and so we have to figure out how far to jump. So if you jump too far, you might actually skip over the minimum and come up with a higher function value rather than a lower one. And so some of the methods to decide this learning rate will adapt based on how much of a difference in the error rate you've gotten. So if you're rolling on a relatively flat period, you might take a bigger jump, while if you're going through a regular steep period, you might take a smaller step. Okay, in order to sort of keep approximately constant the amount of gain you get in the error. And so that's one trick you can do to sort of avoid this decision about the step size. Otherwise, people sort of tune it in an application-specific way. Okay, and if it's too small, then you'll sort of fall within the gradient, but you'll take a very long time to get there, and you have to also doctor in the convergence test as well, whether it's above the threshold. Okay. So what's the point of all this? Well, the cost function is actually pretty general. It can be almost anything, and the model parameters can be almost anything. As long as the cost function can be differentiated, so you don't get sort of stuck in discontinuities as you're rolling down the gradient, you can use this to optimize a lot of different problems. Okay, so a couple of other examples that you'll see in machine learning contexts are these: logistic regression and support vector machines. And you can use gradient descent with these methods. We won't have time in this course to go into these in much detail, and there's plenty of great machine learning courses out there, but I do want to give you intuition for these two techniques so that you sort of calls to mind an image in your head when you hear the terms. Okay, so for both of these cases, you have our vector of weights like we had before, and we have a vector of instance values from our training data, just like we did before. And here we're expressing that as kind of a dot product of two vectors. And in some cases, you need to use the trick where you append a dummy attribute with just constant values of 1 in order to make this dot product work out. But other than that, you've got this kind of setup with these two, and I won't go through these in detail except to call out this funny term over here. We will talk about what that's what purpose that serves in a bit. Okay. So logistic regression, just a quick intuition for what's being accomplished here. If you try to take our regression procedure that we just described and apply it to, say, the Titanic data set that we were looking at previously, you might end up with something like this. Here I've got the x-axis, which is age, and I've scaled this data down so it ranges between sort of -2 and 3 as opposed to 0 and 85 or something, which is the ages of the passengers. And on the y-axis is just 0 if they did not survive and 1 if they did survive. Okay. And now if you just run regression, you know, maybe we could say, well, hey, look, we're gonna create a line and then use that regression line to predict whether someone lived or died. Well, this is the regression line that the gradient descent procedure finds. So what does this really mean, given this kind of categorical data that's been, you know, embedded in a numerical context? Well, probably not much, right? It's not clear that we would really use this line to predict anything. So with categorical variables, even if we kind of give them a numerical interpretation, regression doesn't make necessarily a lot of sense. However, there's a function called the logistic function that is this guy, and it has this nice property that it can map values from -infinity to infinity onto the range 0 to 1. So it gives them kind of a probability, and you can interpret this like a probability. So that very, very high values are interpreted as increasingly likely events. And so you can use this for classification, right? So now instead of a 1 or a 0, you get out a probability of it being 1 or a probability of it being 0. So this has a nice interpretation in terms of probability. It allows you to take a linear combination, well, let's say a linear combination of variables to produce a number and assign that to a class in a reasonable way. Okay, and so the cost function is constructed using the logistic function in such a way as to maximize the probability of a correct classification. And then given these exponentials, it's sort of an easy function to work with mathematically. And this is what it looks like if you plot this. So that's the goal of logistic regression, is to give you a way to work with probabilities in this optimization context. And in particular, you can think of it as useful when you have a categorical output variable and you still want to use these more numerical techniques. So what's a quick intuition for support vector machines? So the context here is finding a line that will separate the two classes. So here we have red dots and blue dots, and this is maybe when passengers survived and when they didn't survive, and we're trying to find a line that separates them. It won't always exist, and we'll handle that case in a second, but imagine for a second that it does exist, that you can draw a line, a straight line that will separate the blue ones from the red ones. Okay, and so we want to find this line. Well, there's various techniques that we won't go into that can walk through and find such a line, but you can imagine that the best such line is one that is in the middle. And how do we define the middle? Well, you can define it maybe by maximizing the margin between the blue and the red. It's the one that maximizes that margin. And so you can write that notion of a margin down precisely, and what you come up with is that cost function that we showed for support vector machines. Okay. That's great. Now, what about the case where it's not linearly separable? Well, what you can do is try to strike a balance between finding a line that gives you a nice fat margin versus one that perfectly classifies the points. And this allows you to maybe find an alternative to this line. So this line does actually separate them linearly, but the margin here is very, very skinny. And so you might imagine that maybe this one's an outlier and should not be considered as part of the, should not be considered a red dot for purposes of classification. If you should be considered an error. And so maybe that this line separates all the rest, say we have a lot more blue ones and a lot more red ones on either side of this line. Maybe it does a pretty good job overall of classifying, and it also has a fatter margin. Maybe we take that one. Okay, so how do we add that term in order to strike this balance? Well, we'll come back to that in a second, but that's that regularization term. So for those cases that are not linearly separable, you can also soften the definition of margin to allow for misclassified points using what are called slack variables. So fine. So these techniques handle, sort of the outlier noise cases, but in some cases there might be a pattern to the data where it's not linearly separable, but it's not because of noisy error why it's not separable. It's because the pattern is not, the two classes are not defined by a straight line between them. And so if we don't, we don't think about the 2D case, now think about just the 1D case. If we've got a group of blue points here in 1D and a group of blue points here in 1D, and then in between them a group of red points, well, there's no one point I can draw that will separate these guys. But clearly there's kind of a group here. What we want to do is sort of draw a circle around this. And so another capability that the formulation of support vector machines allows fairly naturally is to map the data into a higher dimensional space by applying these kernels. And so, for example, here we map all these 1D points into a 2D point onto a parabola, and then we can draw a straight line between them. And so this allows you to turn kind of a nonlinear surface into a linear surface so that we can use the same technique. And again, I'm not going to say too much more about the mathematics there. I just want to give you that intuition for why these are a pretty strong workhorse in machine learning. They're pretty general. Okay, and so going back to our Titanic example, we can see some uses of support vector machines. So here is the linear support vector machine learned on this Titanic data where the attributes I've chosen are P class, or remember class being first class, second class, third class on the ship, and gender. And remember that red did not survive and blue is survived. And also remember that I added some noise to the data just so you could see the blob of red and the blob of blue. Otherwise, the points would be at exactly one, right here in the middle and right here in the middle and so on. So here it finds a line straight between male and female and decided that that was the best linear classifier, which makes sense. But here it learned a more complex surface where it's grouped the first class females and second class females and decided that they survive, and then it split the third class females. Okay, and so if we choose two different attributes in the Titanic data set, given that those were fairly simple categorical data, here is age and first class, second class, third class, and again with the radial basis functions as a kernel, and the support vector machine learns a pretty complex surface, right? Again, everything here in yellow is survived, and everything in dark blue is not survived. And so it, kind of found this little patch over here where it seems to think, because of these two blue dots, that second class and third class and older people from second class and third class must survive in this little narrow range. And it found this one up here that a very old person from first class did as well. But this sort of should smell like overfitting to you, right? When you get this complex of a surface in data that we can sort of look at and see that it doesn't have that much of a pattern going on, this might suggest that something's up. And so, as usual, there's other parameters you can tune on these learning methods to try to avoid overfitting. Okay, and so in these cases, there's a way to balance the complexity of the surface versus the number of misclassified points. And so here's where we've kind of dialed in those parameters in this particular library using, which is Python's scikit-learn. Okay, and so this is a simpler boundary surface between survived and not survived that perhaps has better generalization properties, right? It'll work better if we were trying to actually predict on the test data. All right, so next we'll talk about regularization, which allows you to strike this balance between simplicity of the model and the classification error. Okay. All right, so going back to the cost functions, we're now ready to talk about this regularization term. And to motivate why this is needed, you can think about these high dimensional problems. So image classification would have a separate attribute for every pixel in the image, and so there might be millions of those. Or these text and analytics problems where documents are represented as vectors of terms. There might be 500,000 different terms that may or may not be in the document, and so each one of those gets its own weight. Okay, and so with all these attributes, with all these weights, with all these variables, it's likely that many of them are going to be correlated. So for example, two terms tend to appear together in a document and tend not to appear together in a document. Or, as in this example, pixels in an image. If you look at a pixel on an image and you look at nearby pixels, they're likely to be the same color, right? If you pick a pixel in the green field, the nearby ones are also likely to be green. If you pick a pixel on the black cow, then the nearby pixels are also likely to be black. Okay, and so there's a problem here, because as we're training the model, one way to change the weights significantly and yet not really improve the error much is to make one of these pixels get a very, very high weight and the other nearby pixel get a very, very low weight. And so they'll cancel each other out, and the error doesn't improve much because they're so highly correlated. Okay, and so here in the what's going on here is the model's becoming more complex in some sense, right? It's getting very specialized to your particular problem, but you haven't actually learned anything, right? It's not going to generalize well. And so you need to have some sort of a condition on, well, all else being equal, we prefer simple models, and maybe not even all else be equal. Even if it makes us misclassify some of the images or some of the documents, we'd really prefer simple models because we know that those tend to generalize better than something that's overfit, overspecialized to our particular data sets. And so this regularization term provides this balance. So let's take a quick digression on norms. So a norm is any function that assigns a positive number to the input, with the condition that the only one that's allowed to have a 0 value on the output is 0 itself on the input. Okay. And so you've seen these before, right? This is the L1 norms and L2 norms that are just the magnitude of a vector, right? Is its L2 norm, right? You add up the square of all the values in the vector, and you take the square root of all that. That's a norm, and that assigns a positive number because you've squared it. So L2 norm is perhaps the most common, but L1 norms are perfectly valid as well, and in fact you can generalize this to LP norm, which looks like this. The notation is these pairs of vertical lines, and it means take the sum of all the members of the set from 1 to n, raise them to a power of p, and then take the pth root of that sum. So let's put one more digression on the stack here and talk about cost functions. So we make a prediction and we have our true known values. We want to somehow compute a single number that summarizes the mistakes we've made, summarizes the amount of error. And so the simplest one that we don't tend to use might be this, right? Just subtract your value, subtract the true value from your predicted value and add those all up. Well, this is not usually what you're going to want because, if you're above the value or below the value, you might get canceled out and look really, really good. You might look like you've done a great job. Okay, so that's not a good choice as a cost function. Another one that is reasonable as a cost function might be, well, look, let's just solve the problem and take the absolute value of this difference and add those up. Okay, and so this is sort of asserting that, one error of 7 units in on a particular data item is just as bad as 7 errors across 7 different data items of 1 unit each. And that may or may not be true in your application. And then the error function that we've maybe seen more is to square the error. And so this is asserting that 1 error of 7 units is as bad as 49 errors of 1 unit, except for the fact that perhaps we take the square root. Now, a lot of times we don't take the square root and we just divide by n, or we even divide by 2 in some cases. Okay, and so this is the average squared error per data point. Might be useful when comparing methods that filter the data in different ways so that you get the amount of error per data point as opposed to having the factor of how much data was in there influencing the number. But all of these might be reasonable functions, and I want to point out that these in fact are the L1 norm and the L2 norm. Okay, so they have sort of a natural interpretation of why you might want to make things positive, because maybe you're adding up the error is why you might want to mapping to strictly positive numbers. And they also point out that this one wasn't very good as an error condition, but also it's not a norm because it might produce a negative number. So fine. So this is why these norms come up in different contexts. Pop cost functions off the stack and go back to regularization. Well, different uses of these norms to control the complexity of the model correspond to different techniques that you'll see in the machine learning literature. And again, we're not going to go into a lot of detail here, but it's what we're doing here is we're coming up with a penalty that adds into our error the absolute value of all the parameters, say in the L1 norm case. And so this means that high values of parameters, positive or negative, will increase the cost. And so the optimization procedure will be incentivized to keep that down. And same thing with the L2 norm. It's also mapping to a positive number, and so it gives this penalty to increase the cost when these parameter values get out of whack, either too high or too low. Okay. And in some cases you'll see the squared L2 norm, which is just the L2, sum of squares without the square root. And so there's an enormous amount of work on understanding the properties that these choices have on different types of problems, and we're not going to get into that here. But I want to make sure that you walk away with the intuition for why regularization was important, and which is to avoid overfitting and penalize complex models to get those complex surfaces like we saw with the support vector machine, and what some of the regularization terms are, which are these L1 and L2 norms. Okay, so going back to gradient descent and looking at it as an algorithm, we may notice that we process the entire data set on every iteration. In order to estimate a parameter, we use the old value of that parameter and we modify it by the error estimate computed on the entire training data set. Okay, use that to estimate the gradient. So and this is infeasible for large data sets of the variety that we will encounter fairly frequently in a data science context. Okay. So a variation on gradient descent is what is called stochastic gradient descent. And stochastic, as usual, means probabilistic, means we're going to be selecting something at random. And so in this case, we select a single data point from the training set and use that to estimate the gradient as opposed to the entire data set. All right. And so we just continue on in that iteration as if that one data point was our entire training data set. And on the next iteration, we select another point at random, and so on. Okay, so what you'll be doing here is your estimate of the direction of the gradient won't be as good because you'll only be considering one data point, but you'll be able to compute that iteration much faster, and so you'll get through more of them hopefully. And so a compromise between these two extremes, using the entire data set and using just a single value, is what some call mini-batch gradient descent, where at each step you pick a small subset of points as opposed to just a single point, or as opposed to using the entire data set, and then you continue on as if that subset was your training data set. And so I think all three of these methods, when you look at this algorithmically, are really pretty simple, intuitive variations of each other. Now, they do have some different properties mathematically and statistically, which is why there's been a ton of work on them. But just from a programming perspective, they're pretty minor variants of each other, and they arise in a fairly natural way, just in the interest of almost a performance optimization. Okay. And I'll come back to that point in a moment. But first, let's look at what this kind of an effect this change has on the procedure. So here's an example of where I modified this gradient descent program that produced these plots to use stochastic gradient descent, where I just picked a single value. You can see it kind of, as it walks down the gradient, it kind of wanders about a bit more and doesn't always find the exact correct direction. And so it might take more iterations to get there. And also the error is kind of jumping around at each point. Now, I wouldn't read too much into this particular example. And if you run this a bunch of different times, you'll see a bunch of different patterns. Some of them will converge in just a few steps, and some of them will take a lot longer, and so on. But it does give you a flavor of the kind of cost to using this method, where it doesn't sort of make a beeline for the optimum point, like it did with gradient descent. We're using the entire training data. Okay. And an example using mini batches, This one happened to have sort of a little bit better of an error character, but you can still just see some noise here, and this one happened to take many more iterations to get to the middle. Okay. One other factor here is that as you're changing the method, stochastic, mini batches, changing the size of the mini batch and so on, the learning rate may have an effect here too, right? So here the learning rate is pretty small, so it looks like we're taking very small steps on each iteration. And if it gets too big, it might sort of jump down here to the bottom and then just bounce around for a while, hopping over the medium and not converging. Okay. And so the choice of method with the learning rate is sort of sensitive here, and in some cases for an application you may be doing a little bit of trial and error, and a lot of the research work goes into try to understanding these trade-offs more analytically. All right. So fine. So if that's two different methods for optimizing this optimization procedure, for applying performance optimization to this optimization procedure to handle larger data sets. But we made the point several weeks ago about scalability nowadays is really not about making things a little bit faster here and there. It's really about parallelization, right? Everything has to be parallelized as you scale data up beyond the size that can fit on a single machine, and everything's going that way. And so if you're not parallel, then you don't scale. So how would you parallelize this? Well, everything we've talked about is sort of inherently sequential, right? Because even in stochastic gradient descent, it's very, very fast because it's only processing a single data point, but each data point changes the parameters, and then those parameters are used to compute the next data point. So there's this dependency iteration to iteration. All right. So what would happen if you just did this in parallel without worrying too much about making it sequential? So the result could be nonsense, but it turns out that it's not nonsense, and it could actually converge. And so what some folks have shown, a couple different groups actually more or less independently, and the paper I've cited here is the one that I'd recommend, has this approach called hog wild. These authors name their approach hog wild, which is to parallelize stochastic gradient descent, just take in each of the threads, in each of the independent processes, start trying to update the parameters using a random data point, and you can apply this to mini batches as well. Now, it's unpredictable which order these updates will happen in, and therefore it's unpredictable which values of the parameters you'll use to compute the new value, right? You may have one thread's updates but not have another thread's updates, and so on. But what they were able to show is that you still make progress on this. And so what was kind of fun about this is it came out, very empirically from a student of Chris Ray's working to try to improve performance here and just trying out ideas. And so they said, look, what might happen if we just remove the concurrency control in this parallel program? We just move the locks, right? So we no longer sort of worry about what order things are going in, just let everything update willy-nilly, which is why they kind of called it hog wild. And so it turned out it kind of worked, and it got a good answer, and you applied to other data sets and they got a good answer still. And so they went back and looked analytically and sort of studied whether this would actually converge in most cases, and we were able to sort of prove that it would. But I think one thing I like about this is, first of all, it gives you a parallel method for stochastic gradient descent, which is nice, but it also sort of shows that the exploration and the empirical kind of trial and error approach, doing intuitively what might make sense in some of these cases, is perfectly reasonable. And then it doesn't necessarily tell you any formal guarantees about what you've done, but it might sort of give you a starting point. So how does this actually look like? Well, let's say we have two different threads that are all going to be applying this parallel stochastic gradient descent algorithm. And if we sort of say time is increasing going down the slide here, well, in the first step we update parameter theta 0 from its old values and the current, the old value of theta 1 as well, and we happen to randomly pick the third instance, so x3, and we compare it with y3. And remember, we don't need this multiplication by x3 here out here because this is parameter 0, which is the slope. So there's kind of in times 1.0 here. Okay, and then at time 2, a different thread will see these new values created, that were updated at time 0 and use those to compute a new theta 0 here. And then at time 3, we're still using the original 0th value of theta 1, but we're using the second value of theta 0, and so on. And so it's unpredictable. With only 2 threads, you could sort of see maybe a pattern here if they're interleaved exactly the way I've seen, although there's no guarantee that they would be interleaved in this way. But you can see that it's sort of unpredictable, but the point is, as long as it's generally making progress, it's perhaps the exact ordering, the exact interleaving maybe doesn't matter. They're all getting updated, they're all sort of an estimate of the gradient, and they're all getting closer to that minimum. Okay, so where are we? We've covered some selected topics in a very, very broad field of machine learning, and in particular we've been talking about supervised learning. So we covered rules and trees as representation of certain kinds of hypotheses. We covered combining a set of weak learners to make a stronger learner with ensembles and boosting, and we talked about this optimization technique of gradient descent, along with some applications of it and how to speed it up with stochastic gradient descent, and then how to parallelize it. And so now we're going to talk about a few selected topics in unsupervised learning. So this is a very broad field as well, and we're only going to cover a couple of selected topics that data scientists ought to be familiar with, but it's by no means a coverage of the entire area. So what is unsupervised learning? So if we have these 4 categories of machine learning that are characterized by where the feedback comes from, then unsupervised learning is perhaps the one that stands out the most. So we've only talked about supervised learning, but you can think about all 4 of these. So in supervised learning, the feedback for the learning comes explicitly in the data. In reinforcement learning, the feedback is supplied by the environment. So this is, control theory when you're trying to keep a plane in the air, for example. And in game theory, the feedback comes from the other participants in the system, the other players in the game. But in unsupervised learning, there is no feedback. And so here you're just looking for patterns in the data itself and trying to put them to use. Okay, so maybe almost all work in unsupervised learning can be viewed as terms of learning a probabilistic model of the data. Okay, so applications of unsupervised learning include detecting outliers. So is this factory behaving normally or not? Classification, which is a little different than classification that we talked about, given that there's no class labels, but you might find groups of similar items, and then when you see a new item come in, you can figure out which of among the groups you found previously is this one most similar for, and thereby classify it as within that group. Okay. You can also think about compression and communication. So instead of sending a sequence of AB, 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 AB pairs, you may say, let's just send the sequence AB and repeat 7 times. And so this is a shorter representation of that string. So in all cases, we're identifying these patterns that describe the data and then putting them to use for various services. Okay, so in particular, what I want to do is talk about clustering. And this is by no means the only form of unsupervised learning, but it's the one that you'll bump into quite a bit. Another common one that we're not going to spend much time on is dimension reduction. Okay, so in clustering, there's perhaps no precise definition of what a cluster is, but which is one of the reasons why you see all these different algorithms for different scenarios. But the output is usually the same, which is a set of sets of data items. Okay, so these items may be points in some multidimensional space, and your goal is to group them by similarity. Or the items may be, say, vertices in a graph, and your goal is to find communities that collaborate more closely than other communities, or that communicate more closely than other communities. Okay, so here you're looking at the edge structure of the graph to identify the clusters, but the output is still the same. It's a set of sets of items. All right, so let me give you an example that comes up in a collaboration we have with some oceanographers here at the University of Washington. So in this seaflow device, they've borrowed techniques from flow cytometry and adapted them for environmental monitoring. So in flow cytometry, the idea is to take, it's a diagnostic tool in medical applications, and the idea is to take particulate matter, blood or plasma from the patient, and put particles in that sample through a capillary single file, bounce light off of it, and by the absorption and refraction patterns of the particle, you can sort of work out which kind of pathogen it is. And so in these applications, you're typically looking for one of a small set of possible critters, and so you kind of know what you're looking for. Moreover, it's on a lab bench in kind of a controlled environment. what these researchers have done is taken one of these devices, or well, not one of these devices, developed their own device from scratch, ruggedized it, and turned it upside down and put it on the bottom of an ocean-going vessel in order to, in real time, get a continuous stream of labeled particles representing the microbial populations of the open ocean. And this is completely unknown. You can get some information out of satellite images, but there's really nothing that's known below the surface. There's no real ground truth for measuring this besides very sparse data from direct sampling. Okay, so how this works is, so one of the challenges here, why I said they push them through single file. Here they do not. They actually open up the pipe a little bit and allow lots of particles to go through because the engineering is too difficult to get things to go through single file. When you're underwater and the boat's doing this. Okay, so that's one of the problems. You have to save energy in the engineering problem, but you have to make it up in the data analysis because now the data is much noisier. Okay, so as light shines through this particle stream, it's collected on either side by various detectors, and there's two detectors that work initially to help filter out, to help identify which particles are at the center of the stream and which ones are at the edges, so you can filter out the ones at the edges. And then there's other detectors for various wavelengths of light. And what you can do here is first filter the data so that you only are worried about the particles that were in the middle of the stream, and then you can start inspecting the different wavelengths to identify these clusters that represent different microbial populations. So in this case we're looking at size, nanoplankton, ultraplankton, and picoplankton, and some of the absorption refraction patterns of these different populations are understood. But in the data stream you still need to figure out what these clusters are, and so they apply a clustering algorithm, a variation on a very popular clustering algorithm called k-means, to analyze this data. And so we'll talk about k-means next. So let's talk about the k-means clustering algorithm. This algorithm has some weaknesses, but it's very, very, very popular, in part because it's so simple to understand. So it's a really good one to be very familiar with. So the k in k-means refers to the number of clusters you're looking for, which is the first and perhaps most prominent weakness, is that you have to know this up front. Okay. So imagine you had data scattered in two-dimensional data scattered as in the slide, and you're trying to find two clusters. The way you begin is take the centroid of each cluster and drop it into this space randomly as an initial guess as to where that cluster would be centered. Okay, so maybe we say here and here. Okay. And then the algorithm proceeds as follows. For each point in the data set, figure out which of these two centroids it's closer to. This is closer to this one, that's about halfway, but probably this one. And this one's about half, but we'll say it's over here. And then so this is our initial guess of the clustering. We think that all these points belong to this cluster and all these points belong to this cluster. So now you take the average of all the positions in that cluster to compute a new centroid value and move the centroid there. So for example here, this one will shift this way, and this one will shift sort of this way. So in the second iteration, our two centroids might look like this, and then we just repeat the process. So for every data point, figure out which centroid it's closer to. About halfway, but let me put it there. And this is our guess at time equals 2 for the clusters. And now once again, average all the positions within that cluster to find the new centroid. And so here, these 2 points will pull a little bit in that direction, but most of the points are this way, so it'll probably shift that way a little bit. And similarly with this one, it'll shift this way. And so at time 3, We have a centroid there, and we have this centroid here. And now once again, assign the points to the closest centroid. And recompute the new centroid value. So this one will finally shift into the middle here, and this one will finally shift perhaps a little bit this way. And then at time equals 4, we can repeat once more and find that the centroids in this case don't move that much on the next iteration. And so once the movement of all the centroids is below a certain threshold, they haven't moved much, things don't change much, things have settled down, we stop the algorithm, and that's our clustering. And so in this case, all of these points will be assigned to this cluster, and all of these points will be assigned to this cluster. So you can parallelize this algorithm by splitting the data items across multiple machines. And one of the key ideas here is that the number of centroids is pretty small, or at least small enough to fit in memory, right? You're not typically looking for billions of clusters. And so you can broadcast those to every map task in, say, a MapReduce setup. So in the map phase, the mappers look at each data point and they have access to all the centroids, and they can figure out which one each data point is closest to, and then send that to the reduce phase according to the cluster that it was assigned to. Okay, so all that can happen in parallel. And then on the reduce side, there's one reduce task per cluster, and it can compute the new centroid value. And so there's a bit of a weakness here because one reduce task could have a lot of work to do because it might have most of the data points, and that could be a problem. But in principle, if things are balanced, you might get a pretty good parallel speed up. And the other weakness with this MapReduce implementation is that there's no direct support for this iterative nature of k-means. We have to repeat this over and over again, and so you have to have some kind of external driver program that will keep kicking off MapReduce jobs one at a time. And we'll talk a little more about this in the final week of lectures. So summarizing the weaknesses of k-means, first of all, you have to know the number of clusters up front. You have a fair amount of sensitivity to the initial starting conditions, in that there's no unique solution. Depending on the starting conditions, you may get a different answer. And there's also some sensitivity to the stopping threshold. There's, as is always the case, there's been a lot of work on repairing these various problems, but when someone just says k-means unqualified, they're typically talking about the algorithm we just described, which is sensitive to these issues. Okay, so there's one more algorithm I want to talk about that's less well known than k-means, but it has slightly nicer properties, so it's another good one to be familiar with, and that is dbScan. So how dbScan works is, given points, say, in a two-dimensional space, as always, we're going to look for points that are separated by a distance of no more than some epsilon. Okay, and so if you can hop from one point to another by hopping no more than epsilon at each point, then all those points will be considered to be in the same cluster. And so whenever you need to jump a little further than epsilon, you'll be entering a new cluster. Okay. So in this example, if epsilon is this distance, then we know we can get, I think it's driving me nuts a little bit. These points are within epsilon, these points are within epsilon, and so on. And so you sort of induce this graph over the data, and so all of these, B is reachable from A by hops of no more than epsilon, so all these are in the same cluster. And actually, C is also reachable from B by hops in the same cluster, but D is not, and so D is in a different cluster. So all the solid points are in one cluster, and all of these hollow points are in another one. All right. So there's some advantages here that are kind of illustrated by this picture. So one is it can find non-linearly separable clusters. So right here, there's no line you can draw to separate these two clusters, and yet clearly there's kind of a dense region and another dense region, and so you want to try to draw a curved line. And dbScan finds this naturally, but k-means won't. K-means will sort of find a point, depending on where you start, maybe here and here or something, in which case you'll get clusters like this. Okay. So there is no dependence on a fixed number of starting clusters like k-means was. There's no dependence on starting conditions. You sort of compute this from any of the vertices in the graph and start making hops. There's only two parameters to this. One is this distance threshold epsilon, and the other is a minimum number of neighbors. And what this controls is, like if I find a point way out here in space that doesn't have any neighbors, doesn't, only has a few neighbors, then maybe I just consider that point noise and I ignore it completely. I don't try to put it into any cluster whatsoever. And so here, if you put min neighbors at 0, you'd get this one in its very own little cluster, this one in its very own little cluster, and so on. And so that just it requires extra bit of bookkeeping. It's not necessarily a big flaw in the algorithm. You'll still find the obvious two main clusters, but you can set this second min neighbors parameter to control the extra bookkeeping you have to do to maintain these singleton clusters. Okay. Fine. And then, the core primitive here as it's operating is to find me all the neighbors within epsilon, find me all the neighbors within epsilon, find me all the neighbors within epsilon. And so this operation is amenable to spatial indexing techniques, which can be implemented in log n, so that every lookup requires only a logarithmic number of steps. Remember, as we talked about in the scalability lecture. And so the overall runtime of this is n log n. All right. So some disadvantages here is that it's sensitive to Euclidean distance measure problems. And if you remember a few lectures ago, I made a point to say that whenever you see Euclidean distance, you should be thinking about there's one big major problem with it, which is the curse of dimensionality, right? So as you get a very, very large number of dimensions, Euclidean distance starts to become somewhat meaningless. It starts to get bigger and bigger and bigger, and the data set starts to get sparser and sparser and sparser. The space that it's embedded in is very, very sparse. But k-means also has this problem because it also tends to rely on Euclidean distance. And you actually can define other distance measures and adapt k-means and dbScan both to use them. Okay. And then another problem is that you're kind of making this implicit assumption that the density that defines a cluster is constant throughout the data set. And so this is related to this concept of heteroskedasticity that we talked about that may have seemed a little unusual at the time, but it comes up in various guises in different contexts. So I want to make sure that I mentioned it. So for example, this plot is actually the same one that we generated to make the point about heteroskedasticity in the statistics segments. But what I've done is just cut out some portions of the data here and here. And so now it looks to our eyes like there ought to be 3 clusters here, right? One here, and one here. But dbScan, given its sensitivity to this epsilon number, do you define epsilon such that this cluster is easy to detect, a very small epsilon about this kind of distance, or do you find it a slightly bigger epsilon so that you can capture these kinds of clusters? And if you're not careful, I suppose here I've actually doctored this one where it's probably okay to use the bigger one, but if you're not careful, you'll the density region here may be on par with the distance between these two clusters here, in which case with a small change to epsilon, you might all of a sudden put the whole data set into one cluster. Okay, and so adaptive epsilons, depending on which region you're in, might be something you could think about. All right. And just like with k-means, you can think about how to parallelize dbScan, and the only trick I wanted to point out here is that you need to worry about this halo region around each cluster, or rather around each segment. So here we divide up the space into, say, 4 different processors, and each processor is going to be responsible for that space. And in the middle, internal to this processor, you can run dbScan as usual. But when you get close to the boundary of the region handled by this processor, you need to do some careful bookkeeping. Okay, and so all the ones that are within this boundary region need to be sent to this other processor for comparison to see whether you need to relabel C4 and C6 as part of the same cluster, whether those two clusters are connected by a distance of epsilon or they're not. And so they'll independently find all their clusters, but then you'll merge some clusters when you combine. And you can actually express this in terms of a sequence of MapReduce jobs which I won't go into the details of, but there's some work done by a student here a few years ago to describe and analyze the algorithm here. Okay. So finally, I just want to wrap up with this great picture from the scikit-learn Python library website, which talks about the differences between various clustering algorithms. And we've only talked about two of these. We talked about k-means and we talked about dbScan. And mini-batch k-means is a online version of k-means that uses batch at a time to compute centroids. But you can see some of the strengths and weaknesses here. K-means actually doesn't do that great in any one of these admittedly tricky challenge problems, where here you would probably think that you want this internal circle to be a cluster and this outer circle to be a second cluster, and k-means doesn't quite get that right depending on where you have the starting condition. Meanwhile, these two clusters kind of overlap in space as well. And here, if you have a bad starting condition in between these two clusters, you might put them all in the same cluster. Or really anything, anytime the starting condition is up here and say down here, this one will sort of gravitate towards this cluster and this one will sort of gravitate towards this cluster and end up in the middle, and so on. Meanwhile, in dbScan, this hop from this cluster to this cluster is greater than epsilon, and so you'll do what seems to be the correct thing, which is put the inner circle in one cluster and the outer circle in another. Similarly here, the distance between these clusters is enough where dbScan figures it out. And similarly here. And for the noisy case, dbScan puts all of these points all in the same cluster, which, to our eyes, that's probably the right thing to do. Okay. So I think the takeaway here is that at least in these four challenge problems, dbScan does the right thing in every case. And so it's a good one to be familiar with.